Welcome back. Let's learn about cylindrical coordinates. Alright, so in Calculus 2, you were introduced to a new two-dimensional coordinate system known as the polar coordinate system. And we used polar coordinates to make working with certain types of 2D graphs easier. So this included graphs like circles, rose curves, limaçons, lemniscates, any type of 2D graph that's not really convenient to work with rectangular coordinates. And this same idea will be true in 3D space. While our 3D rectangular coordinate system is nice, and we will use it a lot throughout Calculus 3, there are going to be times where alternative 3D coordinate systems will be convenient for working with certain types of surfaces. In fact, there are two alternative 3D coordinate systems that we can use, and each of them has their advantages, but we are just going to focus on the first of these in this video, which is the cylindrical coordinate system. We'll look at the other system in the next lesson. Okay, but now cylindrical coordinates are heavily based on polar coordinates, and so before we can discuss the cylindrical coordinate system in detail, I think it's important that we do a quick refresh on polar coordinates in 2 dimensions, because if you don't understand polar coordinates, you're not going to understand cylindrical coordinates. Alright, now this is going to be a very quick review of polar coordinates. If you want a full review, feel free to just go back to my lesson in Calculus 2 on the polar coordinate system. Okay, but here's the gist. When working with polar coordinates, instead of having an x-coordinate and a y-coordinate, we work with a radius r and an angle theta, and that is reflected in the actual coordinate system. In the 2D rectangular coordinate system, we have a square grid that we plot our points on, but in the polar coordinate system, we have a circular grid. We have these concentric circles that represent different radius values, and then these lines that pass through the origin that represent different angles from 0 to 2 pi. Or if you like to think in degrees instead of radians, it would be from 0 to 360 degrees. Alright, and so each of these circles represents another value of the radius. The first circle represents a radius of 1, the next circle represents a radius of 2, and the next circle represents a radius of 3, and so on. Alright, this coordinate system would extend out forever, just like your typical 2D rectangular coordinate system. The angle, on the other hand, is measured from the positive x-axis, or what we call the polar axis. It's where we have an angle of 0, so it makes sense that we would measure our angle from that angle of 0. Okay, and so remember that when the angle is greater than 0, we measure that angle counterclockwise, or we go upwards from our polar axis. But if the angle is less than 0, or if it's negative, you measure the angle clockwise, or you go below the polar axis. Alright, that's how I like to remember it. But then for the radius, as I sort of already mentioned, if the radius is positive or greater than 0, you simply just measure out to the circle for that particular radius value. If you have a radius of 1, you go out to the first circle. If you have a radius of 2, you go out to the second circle. If you have a radius in between those two values, like 1.4, you just have to imagine where the circle with that radius would be. It would be somewhere in between the circle for a radius of 1 and the circle for a radius of 2. Okay, so it doesn't have to be integer values, but more often than not, the points that we work with do have integer values. But if the radius is less than 0, or if it's negative, you measure your point as normal, but then you reflect it to the other side of the polar coordinate system. Okay, so typically when I plot a point in the polar coordinate system, I first measure my angle, then I measure my radius, and if the radius is negative, then I reflect that point to the other side of the coordinate system. Okay, or another way you could think about it is you're adding an angle of pi to your angle, or 180 degrees. Alright, so that's how the polar coordinate system works. And so now that we have gone through this refresher of the polar coordinate system, I think we're ready to talk about the cylindrical coordinate system. And honestly, if I was really lazy, I could tell you this next sentence and then just end the video. Because all cylindrical coordinates are polar coordinates, but with a z component. Alright, that's really it. So everything you know about polar coordinates is still intact. All the rules you know about plotting points still apply, except now those polar coordinates have a height. They either go in the positive z direction or in the negative z direction. Okay, so to form the cylindrical coordinate system, essentially what we do is we take our 3D rectangular coordinate system and we replace our traditional xy plane with a polar coordinate system, and we leave the z-axis alone. So you would get something that looks like this. Alright, or another way that you can think about it is we took our polar coordinate system and added a third axis that goes through the origin that is perpendicular to both the polar axis and the vertical axis. And that would also result in this 3D coordinate system right here that we would call the cylindrical coordinate system. Okay, you can see that our xy plane now has a polar coordinate system intact, but our z-axis is the same. It just represents the height of any points within that polar coordinate system. All right, so in our 2D polar coordinate system, our coordinate points looked like this. We had r, comma, theta. But now in the cylindrical coordinate system, we're going to have a third coordinate that creates an ordered triple that looks like this. We'll still have our radius, we'll still have our angle, but then we'll have a z-coordinate, or a value that represents height. All right, so when we go to plot these points in the cylindrical coordinate system, it's essentially a hybrid between the polar coordinate system and our 3D rectangular coordinate system. We'll start by plotting a polar coordinate with a radius and an angle somewhere within these concentric circles, and then take the z component into account. We'll either shift that polar coordinate up to the positive z direction or drop it down the negative z axis. Okay, in other words, we're moving the point above the xy plane or below the xy plane, just like we do for z coordinates in the rectangular 3D coordinate system. Okay, so really nothing here is all that new. We're just combining two concepts we're already familiar with to create a new three-dimensional coordinate system. Something that you want to keep in mind here, though, is that the radius and angle for cylindrical coordinates are still measured the same way they were in a 2D polar coordinate system. And so what that means is that r, the radius, is still the distance from the origin to our point, but if it was in the xy plane. If our point is going to move up or down along the z-axis, then really what that radius represents is just the distance from the origin to the shadow of that point, or you could think of it as the projection of that point in the xy plane, okay? Because if the point is up here somewhere, if it has some height along the z-axis, then the radius is not the distance from the origin to that point, it's the distance from the origin to the shadow of that point in the xy plane. Okay, and you'll see what I'm talking about in just a second when we plot some points within this cylindrical coordinate system. But I do really want to stress that point that r is not the distance from the origin to our point P in this cylindrical coordinate system. It is just the distance from the origin to the projection of our point P on the xy plane. All right, so real quickly, if we were plotting a point in the cylindrical coordinate system, let's say that this is our point P, the way that that would have been plotted is by first measuring our angle from the positive x-axis, which is now right here, not over here, okay? Don't let that trip you up. Our positive x-axis is here. So we'd measure our angle and then our radius. Let's say it's along this circle right here. This x is going to represent the shadow point or projection of our point in the xy plane. So this is where our polar coordinate would have been, but then we want to shoot it out into 3D space, either up or down along the z-axis, okay? And so that's how we would get to our point. So the radius r is this measurement right here, not this measurement right here from the origin to our point. That is not the radius. This is the radius, and this is theta. Okay, and then of course, where that actual point would be above the xy plane is dependent on the z-coordinate. In this case, it would be somewhere up here, as that would correspond to our point. Okay, so that's our basic introduction to working with cylindrical coordinates. Now let's practice plotting some actual points within the cylindrical coordinate system. For this example, we're going to be plotting 5 different points within the cylindrical coordinate system. Let's start with point A. We have 1 pi divided by 4, and then 2. Okay, so 1 is our radius, pi divided by 4 is our angle, and 2 is our z-coordinate. So let's start by just plotting our point as if it was a polar coordinate. All right, let's forget about the z component for now. Just look at the radius and the angle. I'll start with the angle. We have an angle of pi divided by 4. That is halfway between an angle of 0 and pi divided by 2. So I'll say that that is this angle right here. We'll say that that is pi divided by 4. So measuring our angle from the positive x-axis, we would go to that angle, but then our radius is 1, so we will be along the first concentric circle. So if this was just a polar coordinate, our point would be right here where I'm drawing that x. But that's not where this point will be, because this point has a third dimension. It has a z-coordinate. In particular, it is positive 2. So what we have here is just a projection of our point. We still need to take the z-coordinate into account. So the way we do that is by first drawing a line parallel to the z-axis from our shadow point or from our projected point in the xy plane. So that'll look something like this. And then what you want to do is draw a line from the right z-coordinate. In this case, it's 2. We're going to look at that value of 2 along the z-axis. And what you want to do is draw a line parallel to the angle. In this case, that's pi divided by 4. So a line parallel to that would look something like that. But really, you don't have to draw it that far. We're just worried about where those two lines intersect, which is right here. That would be our point A. All right, so that's our first point. Let's move on to the second one here. We have point B, which is 2 pi divided by 3, and then -1. Once again, let's just focus on the polar coordinates first. Let's forget about the z-coordinate for now. Let's just treat this as if it was a polar coordinate of 2 and then 2 pi divided by 3. So our angle is 2 pi divided by 3. That is 2/3 of the way to pi. So we're going to be past pi divided by 2 because that's halfway to pi. So I'll say that 2 pi divided by 3 is right about here somewhere. It doesn't have to be perfect as long as you're in the general area. So that's the angle we're going to be measuring to, but then our radius is 2, so we will be along the second concentric circle. So the shadow of our point would be right there where I drew that x, but now we need to adjust for the z component, okay? This is where our point would be if we didn't have a z component, if this was just a polar coordinate, but since we have a z component, we need to take it into account. In this case, it is -1, so we're going to be going below the xy plane in this case. And so to properly plot that, I'm going to start by drawing a line parallel to the z-axis from that shadow point, and then we want to draw a line parallel to the angle from the z-coordinate. So from -1, if we draw a line parallel to that angle, you'll get something like that, and now where those two lines cross is where our point will be. All right, and so that is point B. Okay, let's move on to point C. We have 3 -pi divided by 2 and then 0. So this is really nice. The fact that z equals 0 should tell you right away, hey, I'm not going to be moving anywhere along the z-axis. This is essentially just a polar coordinate. We have a radius, we have an angle, but no value of z, it's 0, so we're not going to leave the xy plane. Okay, so this one's going to be pretty easy. We have a negative angle though, so you have to take that into account. An angle of -pi divided by 2. So we will measure that in the opposite direction. All of our angles that we have measured so far have been moving in this direction from the positive x-axis. But now we're going to go the other way, and -pi divided by 2 is the same as an angle of 3 pi divided by 2, right? If a full circle is an angle of 2 pi, and you're going in the negative direction by pi divided by 2, well, 4 pi divided by 2 is 2 pi, and if you subtract pi divided by 2, you get 3 pi divided by 2. Okay, so that's how you can clearly tell where you need to go for your angle. So we know we're going to be along this line, but then our radius is 3, so we just have to count to the third circle. 1, 2, 3. This is where our point will be. All right, we don't need to draw an X or anything. That is our point C in this cylindrical coordinate system. Because the z-coordinate is 0, we don't go up or down along the z-axis. That point is just in the xy plane. Okay, so we can check that one off. Let's move on to point D. We have -2, -pi divided by 4, and then 3. This time we do have a z-coordinate again, but let's just focus on the angle and the radius for now. We have an angle of -pi divided by 4, so we're going to be moving this way from our positive axis again, and -pi divided by 4, you would just be moving halfway to 3 pi divided by 2, and really what that is an angle of 7 pi divided by 4, right? Because 8 pi divided by 4 would be 2 pi. So if you subtract pi divided by 4, you get 7 pi divided by 4. So that's the angle that we're at. Our radius is -2, which means that we will be on the second circle, but we're going to be reflecting to the other side of the coordinate system. Okay, so to figure out what angle that is, you can just subtract pi from this angle. That would take you to 3 pi divided by 4. So our angle would look something like this. That is 3 pi divided by 4. And we will be along the second circle, so right here. That is where our shadow point will be, or the projection of our point in the xy plane. Now what we need to do is move along the z-axis, and our z-coordinate is 3 in this case. So I'm going to draw a line parallel to the z-axis from our point, or from the shadow of our point. And then our angle is this line right here. So we want to draw a line parallel to that from our z-coordinate of 3. So we'll draw it like this, and then where those two lines meet is where that point will be. That is our point D. Okay, and if you wanted to, I haven't really been doing this, but you can clean this up a little bit. You can erase those extra lines. You don't really need those. That can sometimes help with the visualization of these points within 3D space. But regardless, that is point D. Now let's move on to our last point, point E. We have the coordinates of -1, -3 pi, and -2. And so now all three of the coordinates are negative, which makes things a little bit difficult, but it's nothing that we can't do. I'll start by measuring our angle, and -3 pi at first, that seems kind of tricky because where is 3 pi in the polar coordinate system? Forget about the negative for a second. Where is 3 pi? Well, what that means is you're making a full circle and then another angle of pi. Okay, so if it's -3 pi, we'd be measuring that in the opposite direction. We would be measuring backwards from our positive x-axis. So we would go a full circle of 2 pi and then another angle of pi. So that does take us to an angle of pi, but then our radius is negative, it's -1, so we would be along the first circle at an angle of pi, but since the radius is negative, we then reflect to the other side, and so now we're back along the angle of 0. So right there would be the shadow point or projection of our point in the xy plane. Now we just need to move 2 below the xy plane, or -2 along the z-axis. Okay, so I'll draw a line parallel to the z-axis from our shadow, and then from z equals -2, I'll draw a line parallel to the angle of 0. And so right there where those two lines meet would be our point E. Okay, I know it's hard to visualize in 3 dimensions where all these points are, but that is at least the process of how we would plot points in the cylindrical coordinate system. I always recommend you start by plotting the point as if it was a polar coordinate, and then just adjusting for the z value. Hey there, real quick, before we get to the next part of this lesson, if you find my tutorial videos here at JK Math to be helpful, then I'd invite you to join my membership site JK Math Plus, where you get access to many perks including bonus content and my exclusive community. The bonus content includes dark mode versions of my videos, extra example problems, and more, while the community is a private space online where you can post questions, have discussions, and study together with me and other members. To learn how to join and see a full list of everything you'd get access to as a member, you can head over to jkmathematics.com/plus. I will have a link for that in the description of this video. Okay, so if you're interested in becoming a member, feel free to check that out. It's a great way to support me and the tutorials I make, as well as a great way for you to learn math better. But for now, let's get back to the lesson. All right, now just like with polar coordinates, we can convert cylindrical coordinates to rectangular coordinates and vice versa. In fact, the conversion formulas are exactly the same as they were when converting between polar and rectangular, because the only difference between a polar coordinate and a cylindrical coordinate is that z-coordinate, right? And that z-coordinate is going to be the exact same in the rectangular coordinate system, okay? There is no conversion there. The z-coordinate of cylindrical coordinates will be the same as the z-coordinate in rectangular coordinates, because the way we measure it isn't any different. We're still measuring how far above or below the xy plane our point is. Okay, so we're going to go through this pretty quickly because I've already derived these conversion formulas in my original video on the polar coordinate system, but the way that we get these conversion formulas is by using a bit of trigonometry to relate r and theta to x and y. Okay, so if you're looking at a particular point in the polar coordinate system, remember we don't care about the z-coordinate, that's going to be the same, so we're just looking in 2 dimensions here. The measurement from the origin to our point P is the radius, the angle from the positive x-axis or polar axis is theta, and then the horizontal distance is x, and the vertical distance is y. So once again, forgetting about the z-coordinate, we would get to this point with an x-coordinate, then a y-coordinate, or by measuring an angle and then a radius. Okay, and then using what we know about sine, cosine, and tangent for a right triangle, which is what we have here, this is a right triangle. Remember the trick SOHCAHTOA, which tells us that sine of the angle is equal to the opposite side divided by the hypotenuse, so that would be y divided by r, and then cosine of the angle is equal to the adjacent side divided by the hypotenuse, so that's x divided by r, and then in each case we can solve for x and y to get these conversion formulas. Y is equal to r times sine theta, and x is equal to r times cosine theta. And then using tangent, we know that tangent of the angle is equal to the opposite side divided by the adjacent side, so y divided by x, which is how we get this formula. tangent of theta is equal to y divided by x. And then using the Pythagorean theorem, we know that the hypotenuse squared is equal to the sum of the other two sides squared. So that's how we get r squared equals x squared plus y squared. Okay, and then finally, this is not really a conversion formula. This is just simply a fact. The z-coordinate is equal to the z-coordinate. That's probably not going to be too hard for you to remember, but I did include it here anyway. These really are just the same conversion formulas that we used between polar and rectangular, except now there's an extra z-coordinate to deal with, but it's really not that hard because it's going to remain the same between cylindrical and rectangular. Okay, so if you have a point in terms of r, theta, and z, you can use these formulas to get it in terms of x, y, and z. And the reverse is true. If you have a point in terms of x, y, and z, you can use these formulas to convert it to be in terms of r, theta, and z. All right, just remember, keep this in mind, when you're converting points particularly from rectangular to cylindrical, you want to make sure that the quadrants and the octants of the points match up. In other words, you want to make sure to use the right angle based on where your point would be in the rectangular coordinate system. And we'll talk about that with our example problem for converting from rectangular to cylindrical, but this is something that you want to keep in mind when doing these conversions, specifically for points from rectangular to cylindrical. Okay, so let's take a look at a couple examples. For our first one, we want to convert the point from cylindrical coordinates to rectangular coordinates. And so that means that this point right here is in cylindrical coordinates. We have 2, pi divided by 6, and then 5. Now, to get an idea of where this is within the coordinate system, I am going to quickly plot it. Pi divided by 6, if we measure that angle from the positive x-axis, that would be somewhere about here. I'll just call this pi divided by 6. The important thing to notice here is that it's not bigger than pi divided by 2. So we know it's going to be between those two angles of 0 and pi divided by 2. But that's the angle we're going to be along, and then our radius is 2. So we'll go to the second circle. That's the shadow, or the projection of our point in the xy plane. Then we want to move it up 5 in the z direction. So if this is z equals 5, if we draw our parallel lines here, it'll look something like that. Where those lines meet is where our point would be. But now, that point is in the first quadrant of the xy plane and the first octant of the 3D coordinate system. Okay, so this point is in quadrant 1 and octant 1. All right, so that's important to keep in mind here. It's not going to come in play in this particular example because we're going to be converting to rectangular coordinates, and that's pretty straightforward. But when we do the reverse in the next example, you'll see where this comes into play. Okay, but to convert these cylindrical coordinates to rectangular coordinates, the first thing you want to do is just write down what are your coordinates. In this case, we know that r equals 2, theta equals pi divided by 6, and z equals 5. And so let's convert our coordinates to be x, y, and z. I'll start with a z because that's really easy. It's still going to be z equals 5. That doesn't change, right? Z equals z. But then for x and y, we want to use these two equations right here. We want to get the x and y coordinates, so we want to use the conversion formulas where you have x equals some expression in terms of r and theta, and y equals some expression in terms of r and theta. All right, so in this case, we'll have x equals r times cosine theta, which will be 2 times cosine of pi divided by 6, and y equals the radius, which is 2 times sine of theta, which is pi divided by 6. Okay, now cosine of pi divided by 6 is equal to the square root of 3 divided by 2. So this is equal to 2 times the square root of 3 divided by 2. Those 2's will cancel out. And so x is just going to be equal to the square root of 3. And then for y, sine of pi divided by 6 is 1/2. So you'll have 2 times 1/2, and 2 times 1/2 is equal to 1. So we now have our three coordinates. X is the square root of 3, y is 1, and z is 5. So altogether, our rectangular coordinates are the square root of 3, 1, 5. And that is the equivalent point in rectangular coordinates for these cylindrical coordinates. That will take us to the same exact point in a 3D coordinate system. All right, and that should make sense because the x, y, and z coordinates are all positive, so we know that that would be in the first octant of the 3D coordinate system, which is exactly where our original point is. Okay, so it's pretty simple to convert from cylindrical to rectangular coordinates, but now let's do the reverse. In this example, we want to convert the point from rectangular coordinates to cylindrical coordinates. So what we've been given here are rectangular coordinates. We have an x, y, and z coordinate. So I'm going to write that down here. We have x equals -4, y equals +4, and z equals -3. Now, if we were going to plot this in the 3D coordinate system, where would that be? Well, if our x-coordinate is -4, that would be right about here along the x-axis. A y-coordinate of 4 would take us to about here along the y-axis, and then we have a z-coordinate of -3. So we'll say that's somewhere down here, that's -3. So given those three coordinates, we know that our point is going to be in this quadrant of the xy plane, which would be the second quadrant, right? This is the first, second, third, fourth. And then we're going to be below the xy plane. So in terms of octants, we're not going to be in the first, second, third, or fourth. We will be in the sixth, because the octant below the first octant is the fifth octant, and then behind that is the sixth octant. Okay, so our point is somewhere down here, and it is in quadrant 2, octant 6. All right, so keep that in mind. That's going to be very important when we go to choose an angle for our cylindrical coordinates. And so now let's actually try converting these rectangular coordinates to cylindrical coordinates. In this case, we want to solve for r and theta, so we want to use these two equations that have r and theta in terms of x and y. I'll start with r. We know that r squared is equal to x squared plus y squared, so we'll have -4 squared plus 4 squared. Both -4 and 4 squared are 16, so r squared is equal to 16 plus 16, which is 32. And so r will be equal to plus or minus the square root of 32. All right, now if you simplify that, r would also be equal to plus or minus 4 square roots of 2, right? 32 as a factor, that is a perfect square, that being 16. So you'd have 16 times 2 underneath the radical, but then the square root of 16 is 4. So you just have 4 square roots of 2. All right, but then for the angle, we'll have tangent theta is equal to y divided by x. And so tangent theta is equal to 4 divided by -4, which is -1. So theta is going to be equal to the inverse tangent function of -1. Now, if you plug that in your calculator, it's going to give you -pi divided by 4. But really what you want to do here is just think about what angles, when you plug them into the tangent function, gives you a value of -1. All right, that's essentially the way I recommend you go about it. That way you really only have to work with positive angles. If you don't know it off the top of your head and you have a calculator nearby, feel free to use it, test some different angles and tangent, and see what gives you -1. But hopefully by this point you're pretty familiar with your trig functions. In this case, tangent is equal to -1 when theta is equal to 3 pi divided by 4 and 7 pi divided by 4. At least when you're looking at angles between 0 and 2 pi. Okay, obviously there's an infinite number of angles where tangent's equal to -1, but we're not going any higher than 2 pi because the polar coordinate system doesn't go beyond 2 pi, right? You do a full circle and that's it. Anything beyond that, you just go back to your lower angles once again. So here's where things get tricky. We have two radius values, plus or minus 4 square roots of 2, and two angles, 3 pi divided by 4 and 7 pi divided by 4. So how do we know which coordinates to use? We still know that z is going to be the same, right? Z doesn't change. We know z is equal to -3. But how do we know what value of r and what value of theta to use for our cylindrical coordinates? Well, actually, there's a lot of different combinations you could choose, but you want to make sure that whatever you do choose puts your point in the right quadrant and octant of the three-dimensional coordinate system. All right, and so looking at these angles, which one of these angles takes you to the second quadrant of the xy plane? Well, it's not going to be 7 pi divided by 4, right? That's nearly 2 pi. That's somewhere over here in the xy plane. 3 pi divided by 4 is a little bit more than pi divided by 2, but it's not more than pi, so that's definitely right there. It's definitely within the second quadrant, okay? And so then to accompany that, you want to pick the positive radius. That way you're not reflecting to the other side. So your cylindrical coordinates here would be positive 4 square roots of 2, and then that angle of 3 pi divided by 4, and then the z-coordinate of -3. That is one possible answer. But there's also other possible answers, right? We could use this angle of 7 pi divided by 4. We would just have to accompany it with the negative radius, right? Because 7 pi divided by 4 takes us to this quadrant, but if the radius is negative, then we reflect back to the second quadrant where we would want to be, okay? So another point that you could have here would be -4 square roots of 2, and then 7 pi divided by 4, and then -3. Okay, so either or here works. Both are correct answers to this problem. And there's even more than that. Really, there's an infinite number of cylindrical coordinates that would take you to that same point, right? If you remember when you first learned about polar coordinates, we really stressed the idea that polar coordinates are not unique. There are multiple different ways to represent the same point within the polar coordinate system. And the same thing is going to be true for cylindrical coordinates. They are not unique. There will be multiple ways to represent the same point in the cylindrical coordinate system. All right, so I believe I did a very similar demonstration in my original polar coordinates lesson, but if we're just looking at the xy plane for a second here, if all of our z coordinates are 0, and we're just looking at our radius values and our angles of theta, we can represent the same point in that plane with a lot of different coordinates. I just have 2 examples for each of these points in this plane right here. Starting with this point, that's at an angle of pi divided by 4, but if you add 2 pi to that, so you have an angle of 9 pi divided by 4, you're still going to be at the same point, right? Because 2 pi takes you from an angle of 0 back to an angle of 0, that's a full circle, and then you go another angle of pi divided by 4 to get to 9 pi divided by 4. All right, so you're still at the same point. Then for this point down here, the radius is negative, so while we would be at an angle of pi divided by 4, the negative radius makes us reflect to the other side, so that's where that point would be. But if we make the radius positive, then we wouldn't reflect, so to get that same point, we need to change our angle to 5 pi divided by 4. Really all we did there was add an angle of pi to our angle to then be able to flip the sign of the radius. Okay, and then for this point down here, if you have a positive radius of 2, but an angle of negative pi divided by 4, you go below the polar axis by negative pi divided by 4, so you're at an angle of 7 pi divided by 4, but you could represent that point by just simply using the angle of 7 pi divided by 4, right? You could just add 2 pi to negative pi divided by 4, and there's your new angle of 7 pi divided by 4. All right, and then finally, with these coordinates down here, that would be this point right here, both the radius and the angle are negative, so we would be at that angle of negative pi divided by 4, or 7 pi divided by 4, but the radius is negative 2, so we would reflect to the other side to get to that point, but we could also represent that by just using that angle of 3 pi divided by 4, and then a positive radius of 2. Okay, so the bottom line here, what I'm trying to get across is that there are a lot of different coordinates that could represent the same point in the cylindrical coordinate system, just like in the polar coordinate system. And so these are the rules that you want to know regarding that fact. The first one is if you have a set of cylindrical coordinates, you can get another set that represents the same point by just adding 2 pi to the angle and keeping the radius and z the same. Or what you could do is negate the radius, but then add pi to your angle, and that would also represent the same point. Now, if you like to look at these things in a more general sense, this is how you would represent it generally. You can find equivalent points by adding any multiple of 2 pi to your angle, or you can find an equivalent point by negating the radius and adding any odd number amounts of pi to theta. All right, so by adding pi or 3 pi, 5 pi, 7 pi, and so on. As long as you're adding an odd number of pi's to your angle and negating your radius, you will end up with the same point in the cylindrical coordinate system. Okay, just make sure that that value of n is an integer. So that's all I want to talk about with regards to points in the cylindrical coordinate system. But as you may remember, in polar coordinates, a collection of points can create polar graphs, which are represented by polar equations, or equations in terms of r and theta. The same thing is going to be true in the cylindrical coordinate system. We can represent the graphs of surfaces with equations in terms of r, theta, and z. Okay, and the reason we might want to do this is because it would make the equations of certain surfaces a lot simpler, right? It's just like what we saw in the polar coordinate system. Certain graphs are made simpler by representing them with polar equations. A prime example of this is working with circles. In the rectangular coordinate system, the equation of a circle with a radius of 2 is x squared plus y squared equals 2 squared, but in polar it's just r equals 2. It's a circle with a radius of 2, so just call it r equals 2. That's the circle. Or if you have a circle that's not centered at the origin, if it's centered at some other point, in rectangular it gets even more complicated. You have y squared plus x minus 2 squared equals 2 squared, but in polar it's just r equals 4 times cosine theta. Okay, so clearly in the polar coordinate system, polar equations can be pretty nice for working with certain types of graphs. And now what I'm going to show you is that there are certain types of surfaces that are easier to represent with cylindrical equations instead of rectangular equations in 3D space. And this is particularly the case when working with surfaces that are directed along the z-axis. Okay, that's kind of an important part of this. The surfaces need to be directed along that z-axis, but once you know that that's the case, then representing that surface with an equation in cylindrical coordinates is a lot simpler than its rectangular counterpart. And so I have a couple examples here for us to look at. First up, we have a cylinder. It's represented by this rectangular equation, x squared plus y squared equals 16. Now, typically that would represent the graph of a circle in 2 dimensions, but remember that we are working in 3 dimensions now. So when you have an equation with only 2 variables, what you're actually working with is a cylinder. In this case, it's a cylinder with the trace of a circle that has a radius of 4 within the xy plane. So we have that circle projected along the z-axis to form this cylinder. All right, and so while this is the equation in rectangular, using our conversion formulas, we know that x squared plus y squared is equal to r squared. So in cylindrical coordinates, the equation is just r squared equals 16, and then if you take the square root of both sides, you get r equals 4. And you don't have to write plus or minus 4 because r equals 4 and r equals negative 4 represent the same thing. All right, remember that in polar coordinates, you really only work with positive radius values, and if it is negative, you just reflect your point. So you're still working within a radius of 4, so plus or minus 4 is not necessary here. R equals 4 is the cylindrical equation for this cylinder. Now, if we move on to one of our quadric surfaces, here we have an elliptic paraboloid. This particular elliptic paraboloid is represented by this rectangular equation, x squared plus y squared equals 9 times z. We could rewrite this to be a cylindrical equation by using our conversion formulas. We know that x squared plus y squared is r squared, so we'd have r squared is equal to 9z, and then we can take the square root of both sides and get r equals 3 times the square root of z. All right, that would be the equation in cylindrical coordinates for this elliptic paraboloid. We don't do anything with that z stays the same because cylindrical coordinates do have a z coordinate, right? It's r, theta, and z. So your cylindrical equations should always involve r, theta, or z. You should never have any x's or y's in your cylindrical equations. But now you can see in both cases, the equations are a lot simpler. We just have r equals 4 compared to x squared plus y squared equals 16. Or in this case, we have r equals 3 times the square root of z. That's a lot simpler than x squared plus y squared equals 9z. All right, I have 2 more examples I want to look at here. Here we have an elliptic cone that is represented by this rectangular equation, x squared plus y squared minus z squared equals 0. But using our conversion formulas, we know that x squared plus y squared is equal to r squared. So we'd have r squared minus z squared equals 0. But then we can add z squared to both sides of the equation and get r squared equals z squared, and then take the square root of both sides and find that r equals z. That would be the equation in cylindrical coordinates for an elliptic cone. How nice is that? It's just r equals z. That's it. The radius at any particular value of z is the value of z. And then if we look at this hyperboloid of one sheet, in rectangular, its equation would be x squared plus y squared minus z squared equals 1. We could also convert that to a cylindrical equation because we know x squared plus y squared equals r squared. So we'd have r squared minus z squared equals 1. All right, and really you could leave it like this. There's no nice way to solve for r in this case. What I will do is add z squared to both sides. So r squared equals 1 plus z squared. But that's it. I'm not going to take it any further than that. You could take the square root of both sides if you wanted to. But the point here is that these cylindrical equations are a lot simpler than their rectangular counterparts. They're going to be easier to work with in certain situations. So it's going to be good to know how to convert from a rectangular equation for a surface in 3D to an equation in cylindrical coordinates for a surface in 3D. Okay, one more thing I want to mention here is that we can also represent vertical planes that contain the z-axis and horizontal planes in the 3-dimensional coordinate system with cylindrical coordinate equations. Okay, so what I'm talking about with these vertical planes is any plane that cuts through the z-axis, right? The z-axis is within that plane. We could represent that plane with just theta equals c, where c is the angle that that plane is directed in. Okay, so whatever angle from the positive x-axis that is right there, that angle c, you would just write theta equals c, and that would represent a vertical plane in the cylindrical coordinate system. Or you could represent a horizontal plane by just having z equals c. This is exactly the same as it is in the rectangular three-dimensional coordinate system, right? If you have z equal to some value, you're going to have a plane that cuts through that value of z in the three-dimensional coordinate system. Okay, so the same thing is true here. All right, and so with that, that is it for this lesson. But if you want to get some more practice working with cylindrical coordinates and converting between cylindrical and rectangular coordinates, as well as converting between equations for cylindrical and rectangular coordinates, feel free to check out my examples video that I'll have linked here on the screen. If you have any questions, feel free to leave those in the comments. But if you don't have any questions, this is all I had for now, so I will see you next time.